All right, today what we're going to do is to take a look at some of the things that we were trying to finish up last week. But before we go too far, let's take a look at these different factor crosses when we were looking at the idea of linkage and recombination. So if we have a two-factor cross, meaning that we have basically two genes that we're looking at, and when we cross them, the results of the once we've done that test cross with the F1, will allow us to kind of get an idea, depending on how many recombinants we find, as to whether or not these particular genes are far apart on a chromosome or not. So when we get a two-factor cross, it tells us about the distance, but it doesn't tell us anything about order. So it's somewhat limited, but it still gives us an idea of how closely together some of these genes might be on a particular chromosome. A three-factor cross is a little bit better because it can tell us both the order and the distance of three specific genes. So when we do a test cross between some individual that's heterozygous for three genes. So here we're using G, R, and W to represent the genes. So in this case, you see on this chromosome, this says that this is homozygous, as the homozygous dominant versions of that gene. Whereas over here, here's the heterozygous, here's the homozygous recessive versions of that gene. And so by looking at this would be an individual that has that is heterozygous for these particular genes. So big G, big R, big W, little w. So heterozygous. So this basically means that we took two true breeding parentals, one that was dominant or true breeding for this condition, the G, capital R, capital W, and we crossed it with one that was homozygous recessive for those same genes, and this would be the F1, right? So this is the first generation that would be heterozygous for all three. So moving on, if we were to look at the gametes of that individual, what we'd see is that this was one possible gamete, and this would be the other possible gamete. And that implies that there's no crossover. But if there is crossover, so looking at this, so during meiosis, if we have during prophase 1 of meiosis, if there's a crossover between the G and the R, then in theory we can get an option or a gamete that would have the recessive form of G plus the dominant forms of the R and W, and then another which would have that capital G with the R and W as being the recessive form. So that's a possibility. There could also have been a crossover between the R and the W, so you can see those here. And the way I've drawn them, they look less likely because this one particularly is so close to the centromere, but it still can happen, and this is just my image, so we could spread this out a little bit. But if we had a crossover between the R and the W, so again, R and W, then theoretically we could get some new gamete possibilities. So here you can see what that outcome would be. If we had both happen, then we have another possibility in that we could have this little g, capital R, W, and the big G, capital R, or lowercase r, and then capital W. All right, that's kind of dizzying, isn't it? So, but this is just showing that if we had a heterozygous adult who was making gametes, and so they had the dominant and the recessive forms of those alleles, and if there is no crossover, then this is what we get in terms of the gametes. But if there was crossover, that means that we could still have the ones you see above here, but also have some new combinations. Now, if you do a test cross, and what you see, remember, a test cross is going to cross these original gametes from this parent with one that you know is homozygous recessive for all three traits. If you see in the outcome that 50% have all of the dominant forms of that trait and 50% have the recessive, then you know that there wasn't any crossover for those particular gametes. So let's take a look. This is what it would look like. So here's the original gametes from that F1 heterozygous parent. Now we're doing the test cross with the homozygous recessive alleles of that gene, or of those genes. And here you can see one parent would be phenotypically, understand, so what we're looking at now is the phenotypes. We're saying that this is going to have the dominant form of all three of these genes, and another one would have the recessive. So that would be a 50% or 1-to-1 ratio, no crossover. If crossover, then we're going to start seeing some of those recombinant frequencies, and those are going to vary. So here's an example. I'm going to bring this all the way up here. So if we had, here's the original parental, right? Here's the gametes. And if we got, this looks like that 50-50 almost, right? So here's the 50-50 of dominant recessive, but keep going because we have more than just this number of offspring. So here we have a GR crossover, and here's the outcome, the number of offspring with those particular genotypes, or really what we'd be able to see is their phenotypes. Coming down here, here's the RW crossover. You can see here there's 100 in that group. And then if both crossed over, so if we got that both the GR and the RW crossover, then this would be the number of offspring that had both of those recombinant traits. So out of 1,000 of these offspring, we can then calculate what the recombinant frequency is by adding up the recombinants. Here you can see individually, we can see what that frequency would be for each one of them. And then if we put them all together, we'd say here's the recombinant frequency total for all of them. But really what's more valuable in some senses to use these percentages here to represent the distance that these genes might be on a chromosome. So we can do that like this. So there are a couple of different ways that could be arranged. If the GR, let me come back up here to show you that would be a 10% frequency of that crossover for that particular recombination. So we know 10, that means that there's 10 centimorgans, which is the unit they use of distance between these two genes on this chromosome. So here's the 10. And then the red-white crossover, or red RW, I guess we didn't say what those represent, is 20. So you can see that here. And so, and the recombination frequency for both of them would have to have some overlap. So that's not shown here. So we could create something so that we could show what that overlap might be. That 2% overlap could be depending on this arrangement. So this is just sort of looking at the distance between the individual alleles based on those recombinant frequencies on a particular chromosome. All right, moving on. Just to recap, so there are traits which we say we're looking at patterns of inheritance, and here's one of them. We did a lot of this with the aliens, so there's autosomal dominant. And in that case, you only need one dominant allele to show the phenotypic outcome would be of that trait. But there's also autosomal recessive, and in order for an autosomal recessive condition to happen, it means that you have to have 2 copies of the recessive form. Now, very often we use that when we're looking at things like this, when we do a pedigree and we see that we're trying to follow, in this case, albinism, to have the trait of being an albino, which would have a number of phenotypic outcomes. So, but what we can see here is that we can do this in a number of ways. One of it is to sort of half shade the parent that is a carrier of that recessive allele, but isn't affected. So this parent here on the left would be a female who is a carrier, marries a male who is not a carrier, and notice they have 2 kids, and the daughter in this case is a carrier. But over on this side, we have a male that's the carrier, female is not a carrier. They have 3 children, and now we see that the son of this couple is a carrier. If these 2 have children, then what you see is we get the condition of albinism in both one of the sons and one of the daughters, and one is not receiving the double dose of that allele, therefore she does not have that. That's one way to look at it. Here's another one. It's basically the same form, though this is still autosomal recessive. And you can just see in this case, we're starting with parents in that first generation that are affected by whatever that disorder is. So this father is, and this mother is. And now we can watch how that can be passed to their offspring. And in this case, notice that you don't even see it in this group's offspring, but once they've married someone who's affected, then that you can see it there. This child who is not affected marries the son of this couple, and you can see that they actually do have one affected child. And then in this case, this son is affected, marries a woman who's affected, and both children are. Moving on. So we've talked about sex-linked traits. Very often they're also called X-linked traits. Not to say that the Y chromosome can't be in play with some of these disorders, but very often it's the X. So here's an example. If it's sex-linked, it can be sex-linked dominant, which means that you need only 1 copy of that dominant form of the allele to be affected. Or it can be sex-linked recessive, meaning you need a double copy of the recessive form of the allele. So if it's an X-linked recessive form of inheritance, that means that the male is always going to have that will always be expressed in the male because he only has a Y chromosome, and so it can't mask or do anything to sort of suppress the X chromosome. It's already there. It's got the capital R. So if it's an X-linked recessive and he receives that allele, then he's going to have that condition. It is expressed, though, if it's a female, if she's a homozygote, right? And it can be passed from her if she's heterozygous, that can be passed from her to her son, which causes him to be affected. So remember that, sorry, I should have made this clearer to myself. This is an X-linked recessive form of inheritance. So we're looking at this one on the right. A female that is affected has to have a father and a mother who are either affected, well, the father would be definitely affected, but the mother would either be affected herself or she would be heterozygous. Remember that human males are considered hemizygous because they only have one X chromosome. So for traits like this, that's it.